Due to the monolithic nature of concrete construction, all reinforced concrete columns are designed to resist axial load and some amount of bending moment. We've already talked about how as the bending moment increases, the axial capacity of the column will decrease. For instance, a column with small amounts of bending moment will be able to support larger amounts of compressive force, and a column with a large amount of bending moment will be able to support smaller amounts of compressive axial force. Failure in any concrete column can occur in a variety of ways. Columns with a large axial compression force will fail by crushing, but other columns that have a large bending moment are likely to fail with the tension steel yielding. Therefore, any particular reinforced concrete column can have a variety of capacities which reflect the certain combinations of axial compression force on it along with the bending moments that are on that column. In this regard, the ACI strength design method is still what we work with, but with columns we need to consider both the combination of the axial compression force along with the bending moment. And this leads us to our topic of this video, which are interaction diagrams. Interaction diagrams are a tool that we will use to help us not only evaluate but design reinforced concrete columns. In an interaction diagram, you'll notice several parts. The shape of the interaction diagram will reflect that there are portions and combinations of axial load and bending moments which will cause failure by the concrete crushing or a compression controlled zone. There are other parts of the interaction diagram where just the opposite will happen, that the steel will actually yield in tension, and we call those tension controlled regions. You have a variety of interaction diagrams in your appendix of your textbook starting on page 670. I guess you could really say the first thing we'd like to do is to determine if a concrete column that we're given, if it's going to be adequate under a certain amount of axial load and a certain amount of bending moment. In order to make this determination, we're going to use these interaction diagrams which have been developed by the ACI. Basically, the interaction diagram is just a collection of points, and each point is represented by an XY ordinate pair. The value for the X ordinate represents the bending moment capacity, and on an interaction diagram you'll see that the X-axis is basically the bending moment axis, and the Y ordinate represents the corresponding axial compression capacity, and again on an interaction diagram you'll see that the Y-axis is the axial load axis basically. The relationship between axial compressive loads and bending moment capacity is always expressed in terms of eccentricity. So instead of saying, hey, my moment is 300 foot kips, we're liable to show a 300 kip axial load being offset an eccentric distance of 1 foot. Again, the focus of this is to just begin to show you the different parts of the interaction diagrams. And so here is one of them. All right. Each individual column has its own individual dimensions and its own individual reinforcement. And if we used specific widths and specific depths and specific amounts of steel, we would have to create an interaction diagram for every problem, and that interaction diagram would consist of a multitude of points. This would make for an infinite number of column interaction diagrams. We don't want to do this. So in order to address this problem, the interaction diagrams have been developed in a generic fashion. So the first thing that you'll notice here is when we look at, for instance, the vertical axis, which I already said was the axial load or the axial compression axis, you'll notice that it's not written in terms of load. Instead, they give it a unitless coefficient named Kn. Now, Kn has a formula, and you can see there, it's Pn, the nominal axial capacity, divided by F prime C times the gross area. Again, similar to that, you'll notice on the x-axis, which I've already said was the moment axis, the bending moment axis, they don't write that in terms of bending moment. They give it another unitless coefficient, this one called Rn. And you can see that Rn has its own particular formula. The next thing I would tell you to notice about the interaction diagram is that each interaction diagram is set up for a particular type of column. Again, this is keeping in line with the generic nature. They're not going to say, hey, this is an interaction diagram for a rectangular column 12 inches wide and 20 inches deep. Instead, what they're going to do is they're going to show, an interaction diagram, in this case with 2 layers of steel and a depth of h. Okay? You'll also notice that every interaction diagram is set up for a particular type of F prime C, in this case 4 KSI, and a particular type of steel, 60 KSI. Maybe most important on here is notice the gamma value, 0.6. Remember what we said that meant. That gamma value is saying that the distance between the 2 layers of steel is 0.6 times the overall depth. So again, you'll notice different interaction diagrams have gammas of 0.6 or 0.7 or 0.8, and there's even a variety of ones there. The next thing you'll notice is that there's actually 8 particular curves, okay? And that's not a coincidence that they put 8 curves on here. They put 8 curves on there, getting back to chapter 9, because our percentage of steel can vary from 1% to 8%. Okay, so again, this is a generic diagram. They're not going to lock us down into saying, hey, the area of steel is 3.44 square inches. Instead of doing that, they're going to come up with percentages of steel. And so we actually, in every interaction diagram, we have, even though it's generic, we have 8 individual interaction diagrams. The interaction diagram has a point out here that is sort of where any particular diagram sort of makes a kink. Okay, we talked about part of the interaction diagram being compression controlled and part being tension controlled. Well, this part down here, where below the kink, this is an area that you have tension control. This is an area where the column has so much moment on it that it basically is starting to behave like a beam. So there's various pieces to an interaction diagram, and again, the idea behind these interaction diagrams is that they're generic. So everything's normalized. You'll see 2 steel layers or steel layers on 2 faces. You'll see another interaction diagram to take the case, to give you the case where you have steel layers on all 4 faces. You'll see interaction diagrams with circular columns, and so on and so forth. So this is going to be the tool that we use to evaluate reinforced concrete columns, and then ultimately to design reinforced concrete columns.